Okay, what was that? All right, it looks like we are recording. So 5035 MAA, this is tutorial number 10, and it's our last tutorial of new content. This will be about elastic instability, also known as buckling. So what is buckling, first of all? Buckling is a mode of failure, is a mechanism of failure. So you know that so far you have learned that materials can fail in different ways. They can fail in normal stress, they can fail in shear stress, but there are other ways they can fail. So one failure that we discussed about is the deflection failure, which is not a failure per se of the material. It's more of a safety perception. So if you are walking on a, say, a roof or a floor that is heavily bent, even if it's safe, you wouldn't walk on that because it's heavily bent, because it doesn't look safe, even if it is engineering. So this is also another failure which has to do with perception of safety rather than safety itself. Elastic instability is called like that because you know that materials, when you deform them, they tend to return to their original shape. So they try to resist deformation elastically in the sense that if you remove the load, everything else springs back onto their original shape. What happens though is that sometimes this elasticity is not enough for particular load conditions, is not enough to resist all loads, and then it buckles, it bends. So it changes shape too much for it to be safe. Okay, so and it can't resist the load anymore. So it moves. Well, the best example I can give you about this is spaghetti pasta, which is very stereotypical for me. And you know, it's very, very, very long and thin, and it's very easily buckled. So if you compress it, even a little bit, it bends. Okay, good. Oh, and there's another mechanism of failure of spaghetti pasta that I like very much, that if you try to bend it, when it snaps, it doesn't snap in 2 pieces, it snaps in 3 pieces, always. Yeah. Okay, if you try that, if you try to snap spaghetti pasta in 2, you are not able to. It always snaps in 3. Because as soon as it snaps, the longer part bounces back and it exceeds again the stress, the failure stress, when it snaps again. So always snaps in 3. Try that at home, but in a controlled environment, okay? And then cook yourself some pasta, because you don't want to waste good spaghetti. Okay, so let's talk about buckling itself. So this Euler-Bernoulli description of buckling. So let's start with the deformed shape. So we have a pin and another pin here. The only difference that this pin is on roller. So this is a roller. So you have a pin and roller on this side. And if you push on the roller, for some loads, P, compressive load, so this never happens for tension. This only happens for compressive loads. That means, you remember when you did the truss structures in first year? So some trusses are in tensions, some trusses are in compression, some trusses are unloaded. For the trusses that are in compression, you must not only make sure that this is safe to yield or crushing, it must also be safe for buckling. Okay, so you must make sure that everything is safe in all possible loading conditions. And compressive load means you have to look at 2 failure mechanisms that are competing with each other. So this is the critical load P, and this is what happens if you are at that critical load. So you have some deflection here. This is exactly V of X that we calculated for with Macaulay's method. It's exactly the same, but this, instead of being due to transverse loads, this is entirely due to a compressive load. So how does that work? Well, let's find the bending moment diagram of this deformed beam. And you should agree with me that this is P times perpendicular distance. Now, if the deformed shape is this is the line of action of P, and the perpendicular distance is continuously changing. So depending on which point I'm looking at, the perpendicular distance is different. This is the greatest distance, and here there is no distance. So the bending moment is P times the deflection. Agreed? Because that's what it looks like. And so if I go again into the Euler-Bernoulli description of bending, so you know that the second derivative of the deflection is minus m of x divided by ei. Let's take ei as constant to simplify our lives. So minus m of x is minus p v of x. So I can just substitute this with this, and I end up with this equation. Now, this equation looks suspiciously like the simple harmonic oscillator. Do you agree with me? It looks like you have second derivative plus something times first order term equals 0. And so this is second derivative plus this equals 0. Agreed? This is exactly the same thing. So the solution is always the same. So the solution of this, remember, was something like this, where this is square root of k over m, but now k over m is p over ei. So instead of square root of k over m is square root of p over ei. Agreed? That's exactly the same thing. And instead of having x of t, you have v of x, because that's your unknown here, v of x. Okay, so a and b, remember, from dynamics, these are integration constants. So we have to find these based on the boundary conditions or initial conditions. So in the case of dynamics, were initial conditions, because they were referring to time. Now, in this case, they are space conditions, so we refer to them as boundary conditions. Make sure that you know the difference between initial conditions and boundary conditions. Initial conditions have to do with time, boundary conditions have to do with space. So when you have partial differential equations, like in next year, you will have this thermal diffusion in space and time. So you have partial differential equations, so you have both initial conditions and boundary conditions. Okay. So boundary conditions for this particular case, where it's pinned on this side and pinned on this side, we have that at 0, v of 0, so what is v? This is v of x. So v of 0, well, I used an x-axis that goes from 0 to L. So v of 0 is 0, and v of L is 0. You agree with me? It looks like everything is 0 here and here. So v of 0 is 0, means that sine of 0, this goes away. Cosine of 0 is 1, so b equals 0. That's easy, very easy. And v of L is 0. Let's substitute L here. So v of L is a sine of square root of p over ei L plus b cosine, but b was 0, so we don't care about this because b is 0 anyway. So a sine square root of p over ei times L equals 0. Now this is 0 in two cases. A is 0, but if A is 0, then we are saying that v of x is 0. So there is no buckling. So this is the trivial case is A equals 0. So let's put ourselves in the non-trivial case. So this sign must be 0. When is the sign 0? The sign is 0 when the argument of the sign is m pi, where m is a relative number, which is an integer, which can be positive or negative. So 0, 1, 2, 3, 4, 5, or minus 1, minus 2, minus 3, minus 4, minus 5. Okay? So this is the solution. And so that means that P, which is our load, is now a function of E, I, L, M, M pi. In fact, I can rearrange this to find what is the load that causes this shape. Agreed? And so P is m squared pi squared EI over L squared. So you just rearrange this to find P, and this is called critical buckling load or Euler load. That's why you have the subscript E, because it's Euler. Everything is Euler anyway, because Euler is this Chuck Norris of mathematics, really. So what happens if you change m? See, I told you that this works for every m. Okay, so this works for m equals 0, 1, 2, 3, 4. Well, for m equals 0, you have no buckling again. So this, well, you have, if for m equals 0, you have no load. And so that doesn't make any sense. I mean, it's again a trivial thing. If you have m equals 1, you're looking at the basic shape, mode shape. For m equals 2, you're looking at the second shape. And then you have the third shape and the fourth shape. So you have many, many, many shapes. But see what happens. If m equals 1, you have just this. If m equals 2, you have 4 times what m equals 1 was. So that means that you have some loads for which you can have these shapes. Now, of course, the smallest of them is already a failure. So we don't care about the higher ones. Because if you reach the lowest one, where m equals 1, that automatically gives you the first failure mode, and that means it's already failed. So if you reach this load with m equals 1, it doesn't matter if you go higher, because it's already failed. And that's why Euler load is only when m equals 1, so it's the smallest load that causes failure. That's it. Okay, now let's have a look at different boundary conditions, because this thing only works for pin-pin, which is what we did so far. So I found this one from this, which comes from this. So what happens if I have different boundary conditions? I have fix, free, pin, pin, fix, pin, or fix, fix. What happens in these cases? Well, you have to solve the differential equation again with different boundary conditions, or since we solved it for you already, you don't have to reinvent the wheel all over again. These were already solved. And so we have added a coefficient n, this coefficient n, as opposed to m squared. M squared is the mode shape. So we take m equals to 1, because that's what we are interested in. So m disappears, basically. And you have n here. N tells you what is the boundary condition. So for fix free, n is 1/4. For pin pin, n equals 1, which is exactly this, what we did. For fix pin, n equals 2, and for fix fix, n equals 4. So as you can see, the more you are constraining this, the higher is the critical failure load. So if you want to avoid buckling, over-constrain, basically. So if you over-constrain with respect of a pin-pin, if you use fix-fix, you are making yourself room for 4 times more load to be sustained. Nice. Now, we have a problem here, because compression, that means it can fail in 2 ways. So it can fail for crushing, that means exceeding the yielding stress, or it can fail for buckling. So how do we make sense of these competing things? How do we know? Well, ideally, you should compare the stress, the failure stress for buckling with the failure stress for yielding, and see which one is smaller every time. Is there a better way? Of course it is. There is a better way. First of all, we introduce something that we call slenderness ratio, which is a geometric property of the beam that depends on 2 things: L, the length of the beam, and K, the radius of gyration. Do you remember what that is from year 1? There was one slide in week 7, so many years ago. Yeah, so the radius of gyration is just, so you can calculate it from the second moment of area divided by the area under square root. So it tells you, on average, what is the same, say how far distributed is the area from the centroid. That's the idea. Okay, so you can always find k. If you know I and A, you can always find k. So if you have complete geometric information on a section, you can always find the radius of gyration. So we can rewrite this knowing that I is AK squared. I can rewrite this as this. You agree? So this is AK squared. So I can put k squared here at the denominator. And so I am this L over K, I can call it slenderness ratio. And this only depends on the length and the cross-sectional and the cross-section of the beam, basically. So it's a purely geometric information. So rearranging the equation looks like this, which is easier, I believe, because this is the geometry of the beam, this is the geometry of the beam, this is the material of the beam, and this is the boundary conditions. And so what is the Euler stress? What is the stress, Euler stress that causes buckling? Well, it's just the Euler load divided by the area. And so that's just the same thing divided by A. So it's the same thing without A. Okay, now that we have the compressive stress, which is P over A, that's it. And we have the Euler stress, which is this beast here, we can compare what happens for different slenderness ratio. So I say, what is the stress against the slenderness ratio? First of all, what are the units of the slenderness ratio? It's L over K. Okay? L over K, what are the units of K? Well, I is meters to the power of 4. A is meter squared. So this K squared must be meter squared as well. So this is meters over meters. And so, in fact, we have no units. And this is sigma in megapascal. And so you have the crushing line, which is the first mechanism of failure. And you know that it's P over A, and it doesn't depend on the slenderness ratio. P over A, there is no lambda. So that's constant in lambda. Agreed? And so this goes, and of course, it is sigma yield. If you are here, if you are below sigma yield, you are safe. If you are above sigma yield, you are unsafe. So this is the crushing line. Of course, the buckling stress, though, looks like an hyperbola. It's not an hyperbola, because hyperbola would be lambda without square, without the exponent. This is lambda square, so it looks like an hyperbola, but it's not an hyperbola. And so you have the buckling hyperbolish that looks like this one. So if you plot this one, you get this for n equals 1. If you have n equals 2, you get this and this. It's the same one, but it's just being translated over. Okay. And so, as you can see, if you are in this region, they meet here. If you are in this region, crushing occurs before buckling. You crush first and then buckle. But if you are in this region, you buckle first and then crush. Okay? Because you're looking at increasing the stress in this direction. Okay, so you crush first and then buckle. And if you are here, you buckle first and then crush. All right? So we have identified two regions in this plot. And so we have the crushing region and the buckling region, and they are separated by something that we call the critical slenderness ratio. It's critical because it separates the crushing failure mechanism from the buckling failure mechanism for the same load. If you have the same load, a more slender beam will buckle first, a less slender beam will crush first. All right? Does it make sense? Good. Okay, so what is the lambda critical in formula? Well, it's the critical slenderness ratio for which I told you this line and this line must be the same. So this is the Euler, this one is the Euler stress, sigma E. This one is the compressive stress, sigma C, which is also equal to sigma yield. And so you can just, this is the Euler stress, you can just find lambda for which this equation is true. So you just rearrange to find lambda and you get this. As you can see, the lambda critical depends only on the boundary conditions, this is N, and the material properties, Young's modulus and yield stress. So critical slenderness ratio, it's not a geometric property, although it looks like. So the slenderness ratio is a purely geometric property. But the critical one, it depends only on the boundary condition in the material. And that's a bit of magic, which you can do with mathematics. That means that once you know what's the material and how your beam is constrained, you can already tell, based on your calculated slenderness ratio, based on your geometry, if it's smaller than lambda critical, then it will fail in crushing. If it's larger than lambda critical, it will fail in buckling. The last thing I want to discuss about for this revision is, let's look at this. This is a discontinuous curve. Do you agree? Because the derivative on the left-hand side of this point is different from the derivative on the right-hand side. So this is a discontinuous function. And we don't like them because discontinuous functions must be treated in segments. Segment 1, segment 2. That's what it is. So they are continuous in a piecewise way. So piecewise continuous functions, which are discontinuous in nature. So can we find a continuous function like this? Yeah, of course. It's an approximation, but it works very nicely because it's a continuous function. So we don't have to study it into segments. So is there a function like this? Yes, this one. 1 over sigma failure, which is this red curve, equals 1 over sigma yield plus 1 over sigma E. This is called Rankine-Gordon design formula. It's an empirical formula. It's more conservative because it always lies at the bottom of this line. So it never goes up. So the stress is always more conservative than it should be, which is a good thing for engineers. Okay. For engineers, always go conservative unless you're voting. Okay? Now, this curve tends to sigma yield if lambda tends to 0. So if lambda tends to 0, this tends to this line. And if lambda tends to infinity, it tends to this line, which is very good. Okay, this is exactly what we want. Of course, the most discrepancy will be around here, where you have the actual discontinuity point. Okay, so this is very nice. All right, so we can now start. First of all, any questions? Any questions on this? It's very important. I will stop recording for a second. Not stop. I want to pause the recording for a second. Okay, it's very scary. Okay, we are back again. So let's solve this one. What's this? Let's solve question 1. Yes.
Do you need to continue your recording or you already recording?
Yes, I am recording already.
Okay.
I also got this very loud announcement in this room. Okay, so in a temperature control device, a copper strip measuring 8 × 4 millimeters and 100 millimeters long is pinned at each end. An axial pre-compressive load of 1.33 kilonewtons is maintained on the strip. What temperature rise is required for buckling to occur? Now we are given two material properties. One is the Young's modulus, 100 gigapascals, and one is this alpha. What is this alpha? It says here on top, it's the thermal expansion coefficient. And if you don't know what that is it has units of something per degree. So that something is no units. So it's no units per degree because we're talking about microstrains. We're talking about strains. So alpha is the strain divided by the delta temperature. It's the temperature delta. So it's a material property. Every material has its own thermal expansion coefficient, and it refers to normal strain only. Why? Because if you immerse an object at a certain temperature, it will expand. It will maintain its own shape. It will just expand, get larger. Okay? And that means retaining its own shape means only normal stress. So normal stress in all directions is affected by this. All right, so it doesn't warp, it doesn't distort, unless you have a gradient of temperature. But if it's constant temperature everywhere, then it doesn't distort. Okay, so in this case, alpha is 18 microstrains per degree. It's 18 times 10 to the power minus 6. That's 18 microstrains. All right, does it make sense? Good. Question, delta T degrees Celsius. Shouldn't this be Kelvin?
It doesn't matter.
Why?
I mean, it's delta. The
Okay.
difference is only.
Very good. So yeah, it should be in Kelvin, but every delta T, Kelvin and degrees are the same thing, because from Kelvin to degrees, it's one of the only instances for which you don't have a multiplicative conversion factor, but it's an additive conversion factor. Okay, so when you take the delta, the conversion factor cancels out. Okay. So yeah, you can use this in Kelvin or yes.
So you see for the question, whenever they're given the cross section, is the height always going to be the first number?
It doesn't matter.
Or it doesn't matter?
It doesn't matter. It doesn't matter because it depends on where you take how you take the axis anyway. So. And in fact, you reminded me that we didn't talk about one very important thing is when you have I, which I are you using? Well, of course, since we want the smallest load, you need to use the smallest I. And so that means that the beam will buckle around the smallest I. So in this case, it will not buckle around X, it will buckle around Y. Agreed? Well, it will buckle around X eventually, but when it's already failed around Y, so it doesn't matter. Okay, so these are all the geometrical properties. These are the load properties, and these are material properties, alpha and E. Now, what we want is that this strip looks like this. So it's mounted in this way in this temperature controlling device. And you know that there is a load applied already. It's a compressive load applied of 1.33 kilonewtons. What's required is how much more stress it can take before buckling, okay? And that stress is not due to further load, it's due to temperature only, okay? So what I'm saying is that the Euler buckling load is a combination of compressive stress and temperature stress. Okay, so this stress is due to the compression, and this stress is due to the temperature. Now let's have a look. Euler load is this. Okay, compressive stress is compressive load over area. And temperature one is, well, remember that sigma is E times epsilon. epsilon is alpha delta t, and so sigma t is E alpha delta t. Okay, very easy. Although you need to stitch all these pieces of information carefully all together in order to understand what's going on. Okay, now that we have this, let's have a look at what we know and what we don't know. N is the condition. What is N for this boundary condition?
4.
Second?
4.
4? No, it's not 4. It's pinned at both sides. It's 1. This one. Let me check the chat. It's just glowing orange. 1. Yes, I see Marius. Thank you. Yes, this is 1. So N equals 1 in this case because it's pin, pin, pin. So N is given from the boundary condition. Pi is pi. E is given. Lambda, is it given? Well, we have L and we have the cross-sectional information. So remember, lambda is L over K. And K is square root of I over A. So we know I, we know A, we know L. So we can find. So I can also say that lambda is just L over square root of I over A. Or even better, I can tell you that lambda squared is L squared A divided by I. You agree? So L is given, A is given. Well, A we can find and I we can find. So here we know everything. PC we know 1.33. The area we know. Young's modulus we know. Thermal expansion coefficient we know. The only unknown is delta T, found. That's it. So how much temperature gradient you need in order to activate this strip? Now this is a temperature controlling device, but this is also how some, it's called thermal switches work. So if you know that you are,
In a kettle?
second,
In a kettle?
like in a kettle, yes, also, sure. So a thermal switch works like this. So you have this thing, which is, say, you also have an aluminum thing here, and this is a live wire. So this makes contact. This makes contact with the live wire. This makes contact with the live wire, but when the temperature is too large, this buckles, and it buckles away from the live wire, and so the circuit is not closed anymore. Okay, so it opens, it breaks the circuit, and that's why it's called a thermal breaker or a thermal switch. It's very, very cool. And you're just using the power of buckling to do so. So it's a controlled failure mechanism. And since it's an elastic instability, it's even better because it fails, but when the temperature returns back to normal, it springs back. That's the idea. It's called elastic instability because when you remove the issue, it springs back. So it doesn't fail in a permanent way. Yes?
Do you know what you said about I choosing the height to
Yeah.
be the smallest value?
Yeah.
You said.
It's the smallest value, yes. So let's find what's the smallest value of I here.
So would you use the base as the height, technically?
Yes.
Should the base be?
Yes.
Okay.
So in this case, IXX, let's check which I we want to use. So IXX is BH cubed over 12, and IYY is HB cubed over 12. Now in this case, you do agree with me that IYY is the one that we should use. Agreed? So in this case, instead of I will always say IYY. Every time I find I need IYY, which is the smallest of the two. So IYY is smaller than IXX, so this is the one that we want. Okay, so I will not do the calculations here because boring. Okay, so you do the calculations. I think this exercise is very cool. Now let's do this other one. An aluminium column has a hollow rectangular cross-section of outer dimensions 80 by 50. So let's draw this one. It's a hollow rectangular, so 80 by 50, something like this. Okay. And so let's say that this is the y-axis. And this is the x-axis. Our outer dimensions are these. So let's call this capital B and capital H. And the uniform wall thickness of 10 millimeters. So let's call this one T. The column is rigidly fixed at the bottom and top and free. What, the column? The column rigidly fixed at the bottom and top and free is subjected to an axial compressive load. So we have a condition that looks like this. It doesn't say how much, but we know that the material properties are 84 gigapascal for Young's modulus and yield stress of 180 megapascals. Calculate the critical slenderness ratio. Nice. First of all, what is N for this? It's 1/4. Come on, guys. 4 is for fix. This is fix free. So this is the least constrained one. Okay, this is very susceptible to buckling. So N is 1/4 for the fix free boundary condition. And what is the critical slenderness ratio? Do we need anything? We don't need anything. We need to know the material properties and N and the boundary conditions. Let's take this one here. That's what we need. There you go. Bam. How much is this? I believe this one is 33.9. Just make sure that you use the correct units. E is in gigapascal, so you want to be using megapascal. So it's N is 1/4 times 84,000 divided by 180 under square root times pi. This should give you 33.9. What are the units of this? No units, because it's megapascal over megapascal. That's it. Nice. Using the Euler buckling formula, calculate the maximum compressive axial load that can be applied to the column if the height of the column is 7.5 meters. Now the height of the column is the length of the beam, basically. And so I'll just copy and paste the formula for the critical load. So this is Euler load. This is part A. This is part B. That's it. So we first have to calculate the slenderness ratio. Now the critical one is this. And now we calculate the actual one to see if it's greater or smaller than the critical one. If it's greater, it will fail in buckling. If it's smaller, it will fail in crushing. So lambda equals L over K. And L is given and K is not given. So let's find K. So K, let's find K first. K is the square root of I over A. Therefore, let's find I. Which one is the smallest I in this case? Again, it looks like it's around Y. So it's I, Y, Y is the smallest one. How much is that? Remember, the area that we want is this. And so we want I, YY is HB cubed divided by 12 minus, so it's the larger square minus the smaller square. Okay, so the larger square is HB cubed divided by 12, where B is 50, where B is 50, and H is 80, and T is 10. So you know that the small b here, so small b and small h. Small b is capital B minus 2t, and small h is capital H minus 2t. Again. So this minus small b, small h, small b cubed divided by 12. Agreed? And so can you do this calculation for me, please? Where this is just hb cubed divided by 12 minus h minus 2t times b minus 2t cubed divided by 12. Can you do this calculation for me, please? And also, what are the units of this? Same of what?
The meter.
Yes. So in this case, millimeters to the power of 4, but yes. Give me a number, please. Let me check the chat. Probably have the chat here. Asia says 698,333. So let's say 698,333.3. Well, it's already millimeters to the power of 4, so let's take it like this. Approximately just 698,333. Yes.
How do you go from HB over 12 minus HB over 12?
Because I'm looking at these. So this small b is capital B minus t minus t. Okay, and also small h is capital H minus t minus t. Okay. Okay, we have this, and can you tell me how much is K then? So the area of this is also, so the area is HB, sorry, B capital B times H minus small b times small h. So can you tell me how much is the area in millimeters squared? Come on, who's faster? Guys, this is easier than the last one.
2200.
2200. Thank you. Millimeter squared. Okay, so how much is K then? How much is this? And what are the units of this? The units are millimeters.
2 millimeters squared.
No, it's because it's under square root.
17.82.
17.82. Okay. So how much is lambda then? It's 7.5 meters in this case. So it's 7,500 millimeters over 17.82.
421.
421. 421. And this is no units. Okay. Make sure that you know. 421. 421. Okay. Now we have lambda. We have lambda. We have n, it's 1/4. We have pi, of course we do. We have e, we do. We have a, yes we do. 2200. We can calculate p. How much is p? It should be 0.5 kilonewtons of 500 newtons. As you can see, only 500 newtons, which is about 50 kilograms. So P is n pi squared EA over lambda squared, which is 500 newtons. And why it's only 500 newtons? Because the slenderness ratio is unbelievably high. It's too slender. It's 421 longer than it is thick. It's 421 times longer than it is thick. That's the idea. So this is actually, it might be spaghetti, 7.5 meter long spaghetti. I'm hungry. Part C, using Rankin-Gordon equation, calculate the maximum height of column that will survive under an applied load of 5 kilonewtons. Now this is 5 kilonewton load. So what is the maximum height of a column that can survive, that means doesn't fail, an applied load of 5 kilonewtons? It doesn't fail either in compression, in crushing, nor buckling. So it's the same dimension. We need to find what's the new height, what's the new length of this, so that it doesn't crush under 5,000. How much? It's 5,000 newtons rather than 500 newtons. Okay, so we need 10 times as more. And how much shorter it must be, because of course it must be shorter now in order to survive that load. So for part C, yes, we start from Rankin-Gordon design formula, this one. And then we have sigma F is the failure. And an applied load of 5 kilonewton. So sigma failure is 1 over P over A. This is sigma yield, and this is sigma 1 over sigma E. Well, sigma E is just, let me find it here, very easy, this one. So this is n pi squared E divided by L divided by K squared. Okay, so the only unknown in this equation as you can see, is L, because this is the new load, 5,000 newtons. This is the area that we know. This is this we know. This is the same cross section, so it's this K is also the same. And what's the new length so that it doesn't fail? Well, so that we are on the brink of failure, really. Okay, so under that length it will not fail. Above that length it will fail. Okay, any questions on this? As you can see, it's very easy. How is P500? Actually, for lambda use, I use this one. I used 421. And remember, you have to use the correct units. So if you use E in megapascal, A in millimeter squared, and then you should get a result in kilonewtons. So you should get 0.5. Here is this. Good. So remember, what you get is a result in kilonewtons here, of course, because you have megapascal and millimeter squared. So of course, you will get you will get an answer in newtons, I think. Yes. Yeah. Okay. So make sure that you know what you're doing with the units. Did you understand this? Okay, it's very simple. This is the failure stress. So the only unknown here is L, which is your new L, so that you have these things. Okay, I think we don't have time to do this, but I'll probably just tell you how to go about this. So we have a 1.2 meters long steel strip of this rectangular cross-section subjected to an axial compressive load. The strip is mounted horizontally with a 10 millimeter edge vertical. So the left end is rigidly fixed, and the support at the right it can free to move horizontally, but restrained between two fixed guys to prevent rotation in the vertical plane only. So what you have is that you have different conditions. You have different conditions for X and Y. So X and Y, you have different boundary conditions. So it can rotate. So it's pinned around X, but it's fixed around Y. So you have to do this analysis twice, around X with a certain N, and around Y with a different N. It's also in the examples of the lectures. I've seen it. It's one of the last examples of the lectures is very similar to this one. You have to make sure that you understand what are the fixing conditions in both planes of bending, because it can bend in one way, but it can also be constrained in different ways in two different planes. So estimate the Euler buckling load. The Euler buckling load is the smallest load for which it fails. So depending on which you look at the XX and YY planes, different boundary conditions, you take the smallest load, and that's the Euler buckling load. And then it says, if we release one of the constraints, what's the new Euler buckling load? Is of course, it becomes higher. Oh, no. We are over constraining this. So we are not releasing the constraint. We are adding a new constraint. Of course, the Euler buckling load goes higher, and it's 4 times as high, as you can see. Very easy. For the end fixing condition in B, what's the maximum safe load that can be applied using Rankine-Gordon formula? So again, this is exactly the same thing, you just have a different unknown. And now critically comment on any discrepancy between the results in B and C and the validity limits of the Euler theory. Okay, so all this information you find in the lecture slides. Any questions? No? I think this exam question is quite fun as well. It's not too hard. It requires some initial thinking about understanding the boundary conditions and about understanding what is the smallest second moment of area that you have to use. It might be that XX and YY are on different boundary conditions, so keep your eyes out for this. And that's it. Everything else is just literally very easy. If in the exam question they ask you the ranking Gordon formula, it might be worth also drawing this plot here. This plot here, so that you know what you're talking about. This function here is this red curve. If you plot this sigma f as a function of lambda, you'll get this. Okay, so since you don't have any more questions, I think I'm going to give you 5 minutes break. We can even make 10, but 10 is too much, otherwise you lose yourselves. So I'll give you 5 minutes break, and then we'll start revision of solid mechanics. And then we might finish a bit earlier than usual. Okay, so 5 minutes break. So you have 10 past 12. When I use the area 20 to 100 millimeters squares, I got this one, which is the same as in tutorial solutions. Also in tutorial solutions, they work with different, I call it P, not P. Oh, P is P critical. So Euler load or critical load is the same thing. So if you look at how I called it, P, I called it critical buckling load, also called Euler load. So this is exactly the same thing. Now I'm not sure about why you got a different answer, or we probably I didn't do this calculation, so probably this is wrong. Guys, can you please recheck this calculation for me? Because this is seemingly not correct. If we get all of these, this is not 0.5 newtons. I'm so sorry, 0.5 kilonewtons. But apparently the solutions got the same answer as here is getting. So I don't know. Okay,
Yeah, I got the 2572.
okay, so you also got 2572.6. So let's use yours. So 2572.6, which is the same as the solutions apparently, but not the same as this answer here. Who knows?
But they'll probably go for it's like individual. Do you have any more useful suggestions for the report, like the temperature or
So the one very overlooked source of error for strain gauges is how you glue them. If you glue them slightly off axis, you are measuring a different strain. So it depends on the angle you're gluing it on. So you must be spot on to measure this line of stress rather than this. Okay. Also, did you write about the Wheatstone bridge?
No, why would I write about it?
Because it's very important, because that's how you are measuring the strain. So you're not measuring the strain, you're measuring a resistance.
Yeah.
So how do you measure resistance? With a Wheatstone bridge?
Length.
No, it's not just length. That's how you calculate resistance. You are measuring resistance. It's a different thing. If you glue it in this direction, it will measure the strain in this direction. So if you glue it a bit off axis like this, you're not measuring this, you're measuring this. And so you're measuring a different thing that you want. So there's a source of error.
Okay, so maybe I'll...
So now it's 5,000 words, isn't it?
No, I currently have 700, and then broke everything, all the graphs, and still references and everything. So I need to write more.
But you missed the Wheatstone bridge. So,
I mean, I did miss it directly. I didn't write it perfectly because I didn't find it necessary.
I think it's quite interesting because it's part of the setup it's in that magic box that you weren't allowed to look inside, but in that magic box there's a Whitcomb bridge.
Yeah, the lab, the piece of paper that we got at the beginning of the lab. Like 3/4 of it was about the
Whitcomb bridge.
For some reason.
Probably because it's important.
But they give also like different configurations of it, like the inside. No, like that's the question. This one better, like how does help?
Because with the Whitcomb bridge, depending on how you mount the resistances, you can measure only the bending strain or only the axial strain, even if you have both loads at the same time. That's very interesting. So it's very hard to discern or discriminate which one is the bending stress and which one is the axial stress, because they are both normal stresses. You're measuring both at the same time. But with a certain arrangement of Whitcomb bridge, you can make sure that you isolate one or the other. It's not, because aluminium is a linearly elastic material. And so everything that is a discrepancy with this linear elastic behavior must be due to error. Okay, I think it's time we resume. It's 5 minutes already. So. All right, so do you want me to solve anything in particular? First, this is revision, so it's kind of open-ended, open questions. So do you want me to solve anything in particular, or do you want to go? Yes. Yes. I don't think so. But again, it doesn't matter, because the words in a table, how many words?
It takes up quite a lot.
You okay?
It takes up quite a lot, doesn't it? At least like big, that's like concrete. What?
What's going on? Is it exploding? But hopefully not. Is the fan kind of loud? The question, can you do it the IJK way? What is the IJK way?
Cross product.
Oh, okay, sure. Yeah, we can do that. Yeah, that's how you should do it. It's just vector products. So do you know about IJK? I think you do, because you're asking me about it. So you have I, J, K. You know about this, do you? And so if you have I vector J, you get K. I vector J gives you K. K vector I gives you J. And J vector K gives you I. Now, of course, cross product also means that if you invert these, you have the negative, you have the opposite of it. So you have the mathematical opposite of it. So K times J gives minus I times K gives minus J, and J times I gives minus K. Okay, so let's do this.
Which week is this?
Second? Which week is this? I can't remember. I think it's week 3. It's about week. This is combined loadings. So it's about week 3. which is not week 3, it's week 3 of the solid mechanics. So it should be 2 weeks ago. Okay, it's week 3 of solids. So we also have that the moment is, remember, it's force times perpendicular area, but it's also the vector moment is the distance cross product with the force. Okay, good. How does this compare to force times perpendicular distance? Do you know about that? So let's say this is O, the pole reduction of the moment. Let's say the moment about O. And so this force is applied, say, here at point P, and it's in this direction. So, well, this is not. Let's say it's in this direction. Okay. Now, if I do this, this is my force, and this is my R. Okay. Now, as you can see, force times perpendicular distance, it doesn't look like we are doing force times perpendicular the distance here, because this is not perpendicular. So the perpendicular distance is this. You agree? Come on. There you go. And so let's check what this means. This means, remember, the magnitude of this vector, so m in magnitude, is the magnitude of the first vector times the magnitude of the second vector times the sign between the two. Agreed? And now, if you look at this, you tell me what is r sine theta. This is the hypotenuse of this triangle. Agreed? And so r sine theta is this thing here, is this edge. And this edge is the perpendicular distance. There you go. So I can say that MO is F times D. So this is the other way you do the moment. So it's either moment is force times perpendicular distance, or the vector product of the distance from the point of application of the force to the pole of reduction, R, times the vector force itself. Very good. And now let's solve this one. So we have an L-shaped component. It's made from a circular bar with diameter 46 millimeters. So we know that this thing looks like this. With a 46 millimeter diameter phi. Let's call this D. And this is the center. It's fixed at NA and loaded in all triaxial direction at MC, as shown in figure Q1. Calculate the plane stress at the most stressed point on the component and show them on an infinitesimal. Calculate the principal stresses. If the yield stress is this much, does the component fail according to the von Mises failure criterion? And if not, what is the factor of safety? Very good. So it just comprises everything that we did in that week, basically. So how do you do this? Remember, you have to find, you always have first have to find the bending moment diagram. And I believe that it's very complicated here because you have three forces. But you also know that the most stressed section will be here, because that's where the fixed support is. And so you can just take all the forces components. These are all the internal loads. And then you have a force along X, a force along Y, and a force along Z, a moment around X, a moment around Y, and a moment around Z. Some of these will be normal force, some of these will be shear forces, some of these will be bending moments, one of these will be twisting moment. We just have to check the axis. So now the section we want, the section that we want is this one. And so the normal direction of this section is, which axis is normal to this? Yes, Z. Okay, so the axis that is normal to that section is Z. So if I draw the axis here, I see that the x-axis goes in this direction, and the y-axis goes in this direction. Very good. Now, question. Let's find the moment. Now, the moment of these three forces about this point, let's call this point A, so M of A. I want to find the sum of moments M of A. Sum of moments about A of these forces. Now, let's do this in the IJK way. So this is R, let's call this 1 times F1 plus R2 times F2 plus R3 times F3. You agree with me? Okay. So how much is R1? Well, you should agree with me that R1, R2, and R3 are in the same, are exactly the same. R1, R is this. Sorry, the other one. R is this. This vector here is R. Okay? Which is the distance from the point of application of the force, which in this case is all three forces are applied at the same point. So R1, R2, R3 are just R. Okay? R equals R1 equals R2 equals R3. And then I'll say that this is force 1, this is force 2, and this is force 3. Okay? They are all applied at the same point, but they have different. So how much is R in vector form?
600 plus 400 pi.
Yeah, so what we have is, let me check the chart as well. 447.2, that's the magnitude of R. I am saying R in vector form. Marius, you're right that 447.2 might be the magnitude of that vector, but we don't use the magnitude here. We want the vector description. In this case, we want the Cartesian description of R. So R looks like it's got 600, sorry, it's got 400 along X, 600 along Y, and 0 along Z. Do you agree? So R is 600i, sorry, 400i, plus 600j, plus 0k. Agreed? This is the Cartesian description of R. What is the Cartesian description of F1? F1 looks to me it's only vertical down, so it's minus 2000j. Okay? So first of all, let me remove this because it's useless. It's a 0. F1 is minus 2000 J. This is millimeters. This is newtons.
Another
Yes,
is J
J, yes.
for the Z or the Y.
J is for the Y. I, J, K, X, Y, Z.
Yes, so you put still the wrong thing.
What is wrong?
Because the Y is 0.
The 600.
Oh, you're right. You're right. For R, yes. So 600 is Z. Thank you. So this is K. Thank you. So we have no J in this case because on the y-axis is on the plane XZ. So F1 is minus 2000 J. F2 is plus 2500 K. F2 is plus 2500 K newtons. F3 is minus 1000 I. Do you agree with me? Newtons. Now that we have all this information, we can solve this one. So let's do this one by one. So this is 400 I plus 600 K cross product minus 2000 J plus this one again and this one again. This one is minus 2000 J, this one is plus 2500 K, and this is minus 1000 I. And now how you do this, it's just multiplication. And remember these. Remember these, and you add usual multiplication things. So you have 400 times 2000, it's 80,000. Is it 80,000? So minus 80,000. And I times J is K. See, I times J is K. Okay. Plus 600 times this, so it's minus 2000 times 600 is minus 12,000. No, minus 120,000. And this is probably 800,000. And this is K times J. So let's check K times J. K times J is minus I, because J times K is I. So K times J is minus I. And so minus and minus become plus. See? And then you go on doing all these ones. And then you sum all the I's, all the J's, all the K's. Plus, this is 400 times 2500. So 400, let me do the calculation. 400 times 2500, it's 1 million. So this is 1e6. And I times K is, so I times K is minus J, as you can see. So instead of plus, this is minus. Plus 600K times K. Oh, K times K. What happens if you have K times K?
Nothing. I mean 0.
0. Why? Because K and K are parallel to each other. So the angle between the two is 0. So the sine of 0 is 0. Done. So K and K, you have this nice 0 here. I'll write it down to remind you that nothing happened between this and this. Plus, this is also 0 because it's I and I. And then you have K and I. plus. K and I is J, of course, but K and I is J. Yes, K and I is J. So 600 is minus, so this is minus 600,000. J. So 1 million minus 600,000, sorry, minus 1 point, this is 1.6 D6. Okay, so finally, M of A, the sum of moments of M on A, the vector description of this is 120,000 I minus 1.6, well, 1,600,000 J, and minus 800,000 K. I don't know if this is easier or harder than, but it's automatic. So the good thing about this is that you can program a computer to do this, and it's very easy. And if you don't want to make mistakes, this is also a good way to go. But how do you use this? How do you use this in this now? Well, MX is this one, MY is this one, and MK, MZ is this one. IJK, very easy. So you have one description for all. None. Okay, good. And now let's add the page. Add the page here. Now that we have found sum of moments, so this is, let me do I J and K, and they are here. So you have K, J, and I. All right, and it's exactly the same thing that you can do with the forces, but the forces are very easy because Fx is this, Fx is this, F3, Fy is this, and Fz is this. So let's go back to our description. So Fx, as I said, is minus 2,000. Sorry, it's minus 1,000. Fy is 2,500. Fz is, no, Fy is minus 2,000, and Fz is 2,500. And the moments are 120,000. Or remember, these units here are Newton millimeters. That's why they look huge. They are huge because it's Newton millimeters. If you use Newton meters, they are more reasonable numbers. Minus 1,000,006. And minus 800,000. Now remember, this one was Fx, Fy, Fz, Mx, My, Mz. But some of them are normal, some of them are shear, some of them are bending, some of them are twisting. How do we know? You look at the section. Look at the section first. Look at the section. The section is this. And so this thing is, so Z is the normal force as on the axis, yes. So Z is normal to the section. So Z is the direction of the normal force. So that means X and Y are shear forces. Around Z, so if Z is the normal force, around Z is always the twisting moment. And so around X and Y, we have the bending moments. So we have, this one is N. This one is shear, V of Y and V of Z. Around the shear, we have the bending, My and Mz. And so that means that this one is T. And now remember the stresses. Of course you do. So you can just rewrite everything in terms of stresses now. So this follows the fact that sigma Z, of course, the normal stress is in the normal direction. So sigma Z is N divided by A. Which tau is this? Tau what? Well, for sure it's tau X. So sorry, it's tau Z, because we are on the Z phase. The direction we still don't know. Well, direction Y, because it's Vy. And why did I write X? I said Z, and I wrote X, ZY. Very good. And this is Vy times Qy divided by Iyt. Remember this? And then we have tau, and this is not FZ. Sorry, this is my fault. My fault. Because I screwed up and you didn't stop me. I told you that the Z is the normal direction. So this is Vx. So see how easy it is to screw everything up. So this is the twisting torque. And this is an X. Okay? So I also screwed up here. This one. This one is correct. This one is not. So tau Zx is Vx Qx divided by Ix t. This is sigma Z is N over A. Then the bending moment, the bending stress is also sigma Z, which is Mx over Ix times Y. And sigma Z is My over Iy times X. And this, the twisting stress, we don't know. We only know that it's tie Z and something, because it depends on where we are, which point we are looking at. If we're looking at the top point, then it's tau ZY. If we are looking at the side point, it's tau ZX. Sorry, it's the other way around. If you're looking at the top point, it's tau ZX. If you're looking at the side point, it's tau ZY. Remember this? If this is the twisting torque, T, then this is tau ZX, and this one is tau ZY. Okay? Yes?
How you go back to when you write in tau ZX, how do you know it's tau ZX at that?
How do I know if I use Y or X?
No, I mean like for the shear shift, how do you know to put it like tau ZX, tau ZY?
Because I'm looking, so tau Z, because we are, the normal is always Z. So the first letter is always Z. This is tau X because it's the shear force in direction X. This is tau Y because it's the shear force in direction Y.
Why is the first letter always Z?
Why is?
Why is it always Z?
It's always Z because we are looking at this face, which is in the XY plane, so the normal is Z. Okay? Yes.
Are the moments in Newton millimeters?
Yes, apart from the forces, which are in newtons. So tau Z, we don't know because it depends on the point, is M sorry, T divided by J times R. Now, A, I, X, I, Y, and J are all section properties that we can calculate because we know everything about the section. So remember that A is pi d squared divided by 4. Ix equals Iy for this case, which is pi d to the power of 4 divided by 64. And J, in this case, is pi d to the power of 4 divided by 32. Okay, so these are all the information that you need. We can also neglect the shear stress. Why? Because it looks a very slender beam to me. It's 600 millimeters long and it's 46 millimeter thick. So it's 10 times as long than it is thick, more or less. And so I'd say we can neglect these shear stresses. This one, neglect, and this one. Only the direct shear stress, because the twisting one, you can't neglect because it's high. Okay? So neglect because slender. And now it's just a matter of calculating. So first of all, which point do you think is the most stressed point? So let's copy this. And you tell me which point is the most stressed point. You know what? Let me draw it larger. Come on, which one is the most stressed point? This is the y-axis. This is the x-axis. This is the y-axis. So looking at the moments, it looks like we have 120,000 Newton moment around x, which is this moment here. So let me take this here. Let me take this here. So we have a moment of 120,000 newtons. Are you familiar with the double arrow notation? Yes, you should remember. This is moment around this axis. This is m of x. This is the moment around x, means this, bending down in this case. My thumb is along these double arrows, and so this is bending down. And it's much smaller, so let's make this smaller. This is much smaller than my. Say it's my is 10 times as long. It's very long, this one. So it looks like one point, so these points here, bending up and down means that the most stress points are here and here. For this one, the most stress points are here and here. But you should agree with me that around these points, where you switch from one moment to the other, there is a critical point that feels both effects summing each other out. So let's have an example. The example is, if this is bending up and down, I have tension here, and tension here, and compression everywhere here. Agree? For the other one, which is this one here, I have tension here and compression here. So as you can see, the stress here sums up, and here as well. And here they compensate each other. So the most stress point is neither this nor this, is along this, it's around here. How do I find out? You don't need that. So what you need is just to sum these moments up. So if you take this, this is the sum of two moments. Oh. Okay. This moment here, which is the bending moment, it means that this thing is bending at the same time along X and along Y. So it's bending around the diagonal axis. Agreed? That also means that the neutral axis is rotated. And so this is the neutral axis. This is the neutral axis. Neutral axis. And that means that perpendicular to the neutral axis, you have the largest stress. This one and this one. Point A, point B. This is the most tensile stress, and this is the most compressive stress. Agreed? Well, I didn't take into account the fact that My is negative, so I have to redraw everything here. Why didn't you tell me earlier?
I mean, I said sorry like 2 times and they didn't stop. So
because you should not be sorry. I am sorry, you have to redraw everything. Okay, so My goes in the other way around, so that means that we have the neutral axis goes like that, so this is not the point that we're interested in. And so my neutral axis is this one. There you go. This is my neutral axis. And so perpendicular to the neutral axis, I have the points as perpendicular as I can make it. These are the most stress points, A and B. Now, what are the most stress points? This is bending around this axis, so this is the most positive point, this is the most negative point for bending. How do I find out which direction is that? Well, it's just this angle here. Okay, so how do you calculate this angle? Let's say this angle here, this one. Alpha. Well, alpha is just arctangent of opposite divided adjacent. Opposite is my, and adjacent is mx. Agreed? So you know exactly where the point is. Well, you know the position of the neutral axis. So you just need alpha plus 90 degrees to find what's the direction of the point. Yes. It's bending.
It's been like that, so it's kind of going that way.
Yeah, exactly. So it's bending diagonally.
What's the max be like there? There.
It's bending diagonally. So that means that the most, so it's not bending in this direction. It's bending in this direction. So this double arrow means it's bending around this axis.
Yeah.
So if you put your thumb around it, you bend it, it bends in the perpendicular direction of the axis. Okay. Try that with your right hand, not left hand, right hand. Use your right hand. It's called right hand rule. So you put your thumb along the double arrows, and then you rotate your fingers. Okay. And that's how it bends. So if it bends in this direction, that means it bends like this. Second, the max?
So maximum moment when it's bent.
Yeah.
But on that diagram there, where would the maximum press on that?
Maximum tension at A and the maximum compression at B.
Why would there be an end? Why any pace?
No, because that's the neutral axis. Because it's bending around now. So wait, see, if you rotate this to make it horizontal, if you rotate this to make the neutral axis horizontal, so that means it's bending vertically. Okay. We're having some discussion here around this neutral axis. You online, did you understand all this about the neutral axis? Now, the only particular thing that we are neglecting here is that we have to take, these are the most stress point in bending, and on the edge, they are also the most stress point in torsion. You agree? So they are equally stressed in axial tension compression, so we don't care about that. But they are equally stressed in torsion. The problem is, which direction is tau? Tau is in this direction now. Yes, it's clockwise, but what is it? Tau zx or tau zy? This is tau. Well, let's check. T is negative, so yes, it's going clockwise. So this is tau z what? And this is tau z what? You can split this tau z what into tau zx and tau zy. So you have both components at the same time. Okay. And what's the angle? The angle is alpha. Exactly the angle that you found. So this tau z whatever is a combination of tau z tau zx and tau zy. So tau zx is positive and tau zy is negative in this case. Agreed? And how much is tau z? Well, this angle is alpha. Remember, this angle here is alpha. So you can find that tau zy is tau z whatever, which is this thing from the calculation times the sine of alpha. Don't be scared. Don't be scared. Okay? Don't be scared. When you're dealing with vectors, it's all about combinations, components, all these things. Never new. And of course, you have exactly the same tau z whatever here, which can be split into exactly the same components. So you don't have to redo the calculations because it's exactly the same. Just now, tau zx is negative and tau zy is positive. And then you put them on the infinitesimal. So which infinitesimal are you calculating now? Let's say we are taking the infinitesimal at a. And let's take the infinitesimal as a cube. Because a, let's say we are looking at it like z-axis, x-axis, y-axis. And so you have sigma z from the axial load. So sigma z, which is positive. No, it's negative. No, it's positive. Then you have sigma z from the bending, which is also positive on A, because it's tensile. You also have on the back, you have this and this. And then let's look at the stresses, the shear stress. You have tau zx and tau zy. Tau zx is this on this face. And so it looks like this. And tau zy looks like this. Okay. So as you can see, you can't use a square in this case. Because this is not a 2D state of stress. If you look at the stress tensor here, which is just a collection of sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, tau yx, tau zx, tau zy. So a 2D stress tensor has one row and one column that are completely zero, at least one, well, one, because from 3D you become to 2D. Now this is non-zero. This is non-zero. Tau zy and tau xz are non-zero. So sorry, tau xz and tau, yes, all of these are non-zero. So all of these are non-zero. Sigma x is 0, sigma y is 0. Oh, yes. Can you look at this? No, you can't. You need all three. See? You need all three rows and columns. There is no column or no row that is completely zero. So this means this is a 3D stress state. And you can't deal with this unless it says something in particular. What does it say? No. So unless you want to take new axes, possibly, that's the idea. So if you treat this as tau z new direction, and you put this and you split this into a certain direction, you can say that you have something like this. On A, you have tau z whatever, tau z whatever. Then you have x in this direction. Sigma x, sigma x. And this, and this. Okay? You're just changing your plane, that you're saying that your new x and y axes are aligned with these. This is x, this is y, say. So in that case, everything checks out for you. Okay, so you can still treat this as a 2D stress state, but you have to change reference frame. Does this make sense? Now, then you do exactly the same thing that you did for the Morse circle, for Mises, Tresca, safety factor, those things are, these should be very easy. Well, I'd say that's it, but let's just have a look at this. This is just Macaulay's method, which is what we did last week. So it's just a new one, which is even easy because it's a determinate beam. So it's not even one of the hardest ones. So make sure you revise all these things. Thank you, Lynn. I'll see you next week. And thanks all of you as well. Sorry, this went a bit over the time. And I will see you next week. Let me stop recording first.